All right, let's get started. So today we're going to continue our discussion about MPC. In particular, we're going to wrap up our discussion about persistent feasibility as one of the key properties we want to imbue in our MPC control pipeline. And then we switch to the topic of stability. So not only we want to make sure that the MPC loop has a feasible solution at each point in time, but we also want to make sure that whatever action we optimize for does something useful. In our problem setting, useful means we are stabilizing the system that is converting to zero. We'll then wrap up the discussion with a couple of topics that are of practical relevance, specifically how some of the optimization could actually be computed offline as opposed to online. That was actually a pretty big deal about 10 years ago, where hardware was not particularly advanced yet, and optimization solvers were not particularly advanced yet. So offloading part of the optimization offline was a big deal because it relieved what you had to do online. So basically, it minimized delays. And then we're going to talk about the application of MPC to a slightly more general setting, which is that of trajectory tracking. And I will show you how the MPC formulation has to be modified a little bit to ensure that you have a good tracking performance. Interestingly enough, sometimes people in industry gets it wrong. So I want to make sure that you are not one of those people. All right, so last time we introduced the concept of MPC. It's a bit dark here. Let's leave it at this before the entire setup explodes. So we talk about MPC, I introduced the concept. I introduced a specific problem setup, which is that of controlling a linear time-varying system subject to polyhedral constraints. We talked about the problem persistent feasibility and stability. We introduced some concepts, in particular the concept of a one-step controllable set, the concept of a control invariant set, the concept of a positive invariant set, the concept of a feasibility set. And then we stated the lemma, which reads as if set x1, which is essentially the truncated feasibility set, where we look at feasible state control pairs starting from stage 1 as opposed to 0. Well, if this set x1 is a control invariant set for the system under consideration, then the MPC law is persistently feasible, which means that at each replanning cycle, you have at least one feasible solution. As I mentioned last time, this result per se is not particularly useful because x1 is not one of the tuning knobs that you can manipulate in order to tune your MPC. But we'll see it's a stepping stone for the theorem that I'm going to state in a few minutes that actually relates the concept of persistent feasibility to one of our tuning knobs that is actually the terminal set, XF, that we use as one of the constraints in our MPC formulation. With that context, let's prove this feasibility lemma. The proof is not particularly interesting, but at least it stress tests your understanding of some of the concepts we have discussed so far. So remember that we want to show that, if x1 is a control invariant set, then the MPC law is persistently feasible. So once we transition to the new state, from the perspective of the new state x1, we still have a control that is feasible over the optimization horizon. So the proof is as follows. Remember the definition of a one-step controllable set. So the one-step controllable set to x1, or previous of x1, is defined as the set of states. This is just a definition that we stated last time. Is defined as a set of states in Rn such that there exists a control, a feasible control, such that AX plus BU transitions into the set x1. So that's a definition of a one-step control set. Now, since x1 is a control invariant, again by definition of control invariance, for all states within x1, there exists a feasible control such that AX plus BU is in x1. Now, if we compare the two definitions, we see that x1, a point that is in x1, also belongs to the previous of x1, to the one-step controllable set, is the same property. But a point that is in x1 also has to be in capital X by the definition of x1. x1 is, first of all, the set of states that are feasible, so that are in X. Which means that the set x1 has to be a subset of the intersection between a set X, this is trivial, and the previous of x1. Does it make sense? It's a bit of a mouthful, but it just follows from the definitions. Now, let's go back one step and now reason in terms of set X of 0. So this is the set of states, X of 0, such that there is a sequence of controls such that the states generated under the dynamics are produce states that are feasible. Remember the definition of x0. x0 is the set of feasible states such that there exists a sequence of controls, feasible controls, such that under the dynamics evolution, the generated states are also feasible and satisfy the terminal condition. Now, I can rewrite the definition of x0 as the set of feasible states such that there is a feasible control such that x1 belongs to capital X1, because capital X1 subsumes, where is the definition of capital X1, previous slide, the fact that there is a truncated sequence of controls that lead to a feasible state trajectory. Okay. Now, again, let's compare this definition to the definition here. So they are identical. The only difference is that in here, I'm imposing these additional constraints that the states has to belong to X. So x0 is really the intersection of capital X and the one-step controllable set to x1. But then we put together the two facts, and we see that x1 is a subset of x0. Every state that belongs to x1 is also a state that belongs to x0. Does this make sense? It's mostly basically pattern matching the different definitions. There is no particular cleverness here. Yes?
So the previous epsilon, like it's not necessarily a subset of X.
No, because of how we define it here. Is any state that transition us into x1 could also be a state that is not feasible in terms of set membership to capital X. Okay, so now there is the slightly more interesting part. Actually, this entire proof is quite boring. Take some state that belongs to X of 0, some initial state. And let U star 0 be the solution to the finite time optimization problem, MPC optimization problem. Let U star 0 be the first control in this sequence. Then, under the control U star 0, under the MPC control, we transition into a new state, x1. Since U star 0 is clearly feasible, x1 belongs to capital X1 because it's part of the MPC trajectory, so by definition has to satisfy all the state constraints under the dynamics evolution, and so it belongs to x1. But we just proved that set x1 is a subset of x0, which means that set x1 belongs actually to set x of 0, which means that the new MPC optimization problem is indeed feasible. And then you can recursively apply this property through time. So rewinding all of this, we wanted to prove that under the MPC control law, the new state x1 belongs to X0, the set of feasible states for MPC. To do so, we manipulated a little bit the definition of a one-step controllable set and the notion of control invariance. And we finally proved that if set X1 is control invariant, then the problem, the MPC problem is persistently feasible. Does it make sense? Again, not a particularly exciting result, not also particularly useful, but it's a good stress test for you to see whether you, understand the notion of a one-step controllable set, control invariant set, and so on. In the final exam, there will be one question that where I will ask you what is, say, a control invariant set. Okay. Anyway, so say that the horizon is equal to 1. Then we can just choose the terminal set to be control invariant. And by the previous lemma, we know that if that is the case, then the MPC problem is feasible at all replanning stages. But of course, in general, the optimization horizon is greater than 1. So how can we extend these results to the cases whereby we have a general optimization horizon, capital N? So that's what we're going to do next. Any questions in the meantime? So now we get to the more interesting part. So building on the lemma that I just showed, that says that if X1 is control invariant, then the MPC control law is persistently feasible, now we can prove a more powerful theorem that reads as follows. If the set X of F, which as a reminder is the set through which we specify a terminal constraint for the MPC optimization problem, this is something that we decide. And if set X of F is a control invariant set for the system under study, then the MPC law is persistently feasible. That's interesting. Let's try to understand what this is saying. What is a trivial control invariant set for this system? Meaning a set that if you are there, there exists a control that allows you to stay there. By any mathematical equation, if you are in doubt, always say 0. I mean, typically 0 is the best guess. In this case, it's correct. So the origin 0 is indeed a control invariant set. If your state is x equals 0, assuming that u equals 0 is an allowable control, which is typically true, I mean, doing nothing is typically allowed. Under linear dynamics, if you are at 0 and you use control 0, your next state is 0, which means that the origin, you have a set with only 1 point, but still is a set. The origin is indeed a control invariant set. And intuitively, what is it saying? It's saying that if we just target the origin in n steps, and then I shrink the horizon by 1, there is always an admissible control sequence that is the concatenation of the previous control sequence, and then the fact that with the last control, we just stay at 0. So you can just trivially continue your control sequence to have a full n-step control sequence. So we're going to prove the theorem, but the intuition is quite obvious. That said, for a general system, you might have a different control invariant set. 0 is just an option, but actually you could have a larger set, which is a control invariance for the system. We'll see later how to compute those larger sets. So do you think that the origin is always the best choice? So constraining your system to reach the origin in n step as part of your MPC control law, do you think that this is always the smart thing to do? It guarantees you persistent feasibility, so that's great. Remember that typically you are not just reasoning in terms of controlling the state to 0, but you also want to be very parsimonious in terms of how much control you spend. So oftentimes, asking your system to reach the origin in n steps as part of your MPC optimization problem can be very limiting. So basically, you are asking, so of all the control sequences you could apply, you're only optimizing over those that in n step bring to the origin, which typically are those that require a lot of control effort. So yes, you have persistent feasibility, but now you might control your system very suboptimally, meaning with a lot of control expenditure. So that's why, in general, the terminal constraint, that is something that you artificially add to your MPC problem to ensure persistent feasibility, should be as relaxed as possible so that you don't overly constrain your system. Does it make sense? Just trying to give you both mathematical backing for what I'm saying, but also some practical considerations. And this is stuff that people do for real, right? So it's constantly, you know, a little bit of a design choice how to properly set X of F. So now let's prove this theorem. So the proof is as follows. So we prove that if X of F is control invariant, then Xn minus 1, the truncated set where your horizon is only 1, is also going to be control invariant. And then if Xn minus 1 is control invariant, Xn minus 2 is control invariant, all the way to X1. And once we hit X1, we know from the previous lemma that if X1 is control invariant, then the system is persistently feasible, so we can invoke that lemma to conclude the proof of the theorem. So let's start with the first step. So if XF, we want to prove that if XF is control invariant, Xn minus 1 is control invariant too. Xn minus 1 is defined as usual. Now is just a truncated feasibility set where we only reason in terms of a one-step horizon. It's the set of states, feasible states, for which there exists a feasible control, such that under the system dynamics, we have a sequence of states that is feasible. In this case, the last state needs to satisfy the terminal constraint. Now, because of the terminal constraint, we know that, remember that we want to show that this set is control invariant. So the question is, for any state, so any vector within this state, is there a control input that allows us to transition back into this set under the system dynamics? So that's what we want to prove. Now, what we know is that by the definition of Xn minus 1, there exists a control such that Axn minus 1 plus Bu1 is equal to Xn, which belong to the terminal set X of F. I mean, this is by essentially definition of X1. Now, the question is, does Xn, which belongs to Xf, also belong to X1? If that is true, that it means that X1 is control invariant. I found actually a control that allows me to transition back into X1. But for now, the only thing that I know is that X of n belongs to Xf. But from the assumption of the theorem, we do know that X of f is a control invariant set, which means that there exists a u such that ax plus bu belong to X of f. But isn't it that the definition of defines the membership of a point to Xn minus 1? So we have just proved that Xn indeed belongs to capital set Xn minus 1. Don't be mixed up with the subscript. Xn minus 1 is just a definition of a set. It's the one-step feasible set. So the fact that Xn belongs to X minus 1 doesn't tell you nothing in terms of the temporal coherency between the subscripts. So we have just proven that X of n belongs to capital Xn minus 1. So we have just proved that X minus 1 is indeed in control invariant. But then you can apply this argument recursively until to prove that x minus 2 is control invariant, x minus 3 is control invariant, all the way to x1. At the point we invoke the feasibility lemma from the previous lecture, and then we can state the claim that if xf is control invariant, then MPC is persistently feasible. Does this make sense? Again, there's a bit of pattern matching with definitions. Most important thing for you to understand is, and this is a big deal, if the set xf is chosen to be a control invariant set for your dynamics, then your MPC is persistently feasible. Now, the origin is in general a control invariant set, so is a possible choice for your terminal constraint. In general, is a bit suboptimal. So we want to have more sophisticated choices for the terminal set within all the possible ways of defining a control invariant set. We'll get back to this point later, along with a pointer to a computational tool that allows you to compute control invariant sets. And in problem set 3, you'll have a few problems that will expose you to how to use this toolbox in order to compute control invariant sets. I mean, this is my son that brings back bugs from childcare. This is sort of the child is sort of a biological weapon. This is my 445. I mean, I'm a recorder, so I'll stop here. So we're just complaining about the diseases that go around in the childcare. Anyway, so the terminal set x of f is introduced artificially for the sole purpose of leading to sufficient condition for persistent feasibility. Is one of the tuning knobs. And now we know that at least from an abstract standpoint, if we choose x of f to be control invariant set, persistent feasibility is guaranteed. As I said, the simplest choice would be to just pick x of f as the origin, but this is generally undesirable because it excessively restricts the space of feasible control sequences. We'll discuss this choice later in more detail. Now we switch to the other topic, that is that of stability. Now we know at least how to make the problem persistently feasible. The tuning knob that, at least for the scope of this class, we choose for that purpose is the terminal constraints x of f. We have other two tuning knobs, how we select the terminal cost p in our MPC formulation, and how we select the horizon n. So the question now is, can we tune those tuning knobs in such a way that stability is guaranteed? To prove stability, we will leverage the tool of Lyapunov stability that some of you may already be familiar with, but if you're not, no problem. I'll give you a very quick intro to Lyapunov stability. So what does Lyapunov stability say? I will state in a second the full theorem, but first I want to give you intuition. So say that you have a dynamical system. Sk plus 1 equal f of xk. Or maybe in continuous time, you also have x dot equal f of x. Now the question is the system stable? Roughly speaking, if you start close to an equilibrium point, will you go back to that equilibrium point without having trajectories that go out of whack? If this is a ball, this is a stable equilibrium point because if you have a ball and a ball, never got the pronunciation right. But anyway, so this is a ball and this is a ball. And so if you have a ball in a ball, you know that if you start this ball outside of the equilibrium point, then it will start oscillating. And then if you have a little bit of friction, you dissipate energy, you will go back to the bottom of the ball. So it's the case of a stable equilibrium point. If you're here, of course, this is unstable. This is an equilibrium point. So if you put the ball here, it will stay here. But then if you start a little bit farther from the equilibrium point, you will go down. So say that you have a dynamical system and say that you have an equilibrium point and you want to understand if the dynamics are at least locally stable around that equilibrium point. How can you show that? Well, all that you know is that you have an equilibrium point and you have the transition dynamics. So in principle, what you will need to do is to solve for all possible initial conditions around your equilibrium point, your discrete time equation or differential equation, and then see what happens. Now, in general, solving nonlinear differential equation or also discrete time nonlinear update equations is complicated. So for the longest time, this was a big problem. Then there was a guy, Lyapunov, that came in and saying, well, maybe we can say something about the stability of the system without reasoning directly in terms of the evolution of the state. The idea is, if we can say that there is a sum function that, loosely speaking, has a notion of an energy function that decreases over time along the system trajectories, that could tell me something about the evolution of the underlying system. Think about energy being dissipating along the evolution of a system. That means that basically the system inherently is constrained to reach a point of minimum energy because you are dissipating energy. So basically his intuition is, if I don't need to prove that all the trajectory goes to 0, if I can tell for the system that the system is dissipating energy, then probably will converge to some state of minimum energy, loosely speaking. So that's basically what the Lyapunov theorem says. Considering an equilibrium point for a system xk plus 1 equal of f of xk. Equilibrium point means that if you are at 0, f of 0 is equal to 0, meaning that we stay there. Let's consider a set omega, which is close-bounded positively invariant set. This is some mathematical thing that we need, not super important. Let v, referred to it as the Lyapunov function, be a function that has the following property. Is a 0 at the origin, is a positive outside of the origin, and for the evolution of system trajectories starting from omega, then this function decreases along the trajectories. Then x equals 0 is asymptotically stable. So essentially you have this is your v function, v of x. This is a two-dimensional state space. If I can say that along all possible system trajectories, v decreases in value, it means that the state trajectory is going to the bottom, which is the equilibrium point, since v0 is equal to 0. Which again is encoding this notion that you are trying to show that your system is losing energy along the system trajectory. Note how with this theorem, and that's the most important thing, we can claim stability properties without having to solve explicitly the state transition equations or a system of differential equations if you are in continuous time. So that's the main thing about Lyapunov. As long as we can find a function with such a property, then we can argue about stability. Now, you might say, how do I find such a Lyapunov function v? I mean, that's hard. That's actually the hard part. So in some cases, there are some physical arguments that allow you to construct Lyapunov functions, for example, energy arguments. But in many cases, you can use other arguments, and this is the case that we will consider for MPC. Now, if you're interested in Lyapunov theory, it has a very rich theory, so I would recommend to have a look at some of the references that I provided. For the sake of this class, the only thing that I want to say is that there is a tool that allow us to infer stability property for a closed-loop system that entails using an auxiliary function, referred to as a Lyapunov function, and show that under the system trajectories, that the Lyapunov function has a non-decreasing property, namely this property here. So what we're going to do now to show stability is to show that for the closed-loop MPC law, we can find a Lyapunov function so that we can then claim stability for the MPC control law. So the question is, what is this Lyapunov function? And here there is another theorem, but it's the last one for MPC. So, any questions so far? How many of you heard of Lyapunov stability before? Half, okay. Well, in any case, read about it. It's a useful and interesting tool also with, of course, I present it here quite quickly, but also with a rich physical interpretation. Again, main thing that I want to make sure you understand is that it's essentially a tool that you have to infer stability properties about dynamical system without having to resort to the explicit integration of the underlying system equations. It boils down to show that for some choice that you have to come up with of a function v, you have a non-increasing property of the function v. If you do that, then you can infer stability. So we're going to use the Lyapunov theorem a little bit in a mechanical way without spending additional time in explaining its origin. But I do encourage you to do a little bit of reading on Lyapunov stability because it's an interesting topic. Okay, so let me state now the celebrated stability theorem. This is an interesting case whereby for 20 years or so, people applied MPC without any theory. And then in the 90s, people started to develop theory to tune the algorithm in a more principled way. Do you know something that is happening right now with no theory? Deep learning. I mean, nobody knows exactly how it works, but people use it all the time. Who knows, maybe in 10 years, there will be the analog of, I mean, there is some theory behind deep learning, but it's typically for settings that are not really reflective of what people do in practice. So same here, MPC for 20 years, people applied it, just worked well. And then people said, no, actually, we can add some theory. And this is one of the celebrated theorems within this theory. It says the following. Let's assume that we are in a LQR type of setting. So the cost is a two-norm cost, so X transpose QX plus U transpose RU. So we have a quadratic cost. Let's assume that the control penalty is positive definite. We also assume that the state penalty is positive definite and the terminal penalty is positive definite. We assume that the sets X, XF, and U contain the origin and are closed. These, just to make the math be super solid, but it's not the most critical assumption. Let's assume that XF is control invariant. What do you think we make this assumption? Exactly. This is to ensure that at least MPC is feasible. So we got that covered. And let's assume this fourth assumption here that looks very weird. So basically it's saying that there exists a U such that AX plus BU belongs to the terminal set, and such that under this U, CXU plus P of X BU minus P of X is less than or equal to 0. And this has to be true for all X in XF. That's weird. And we'll see how we use this result. But just to gain a sort of intuition, remember the Lyapunov theorem that I showed you before. We want to show that along the trajectory, something has to become negative. Here, basically, what we want to say is that there exists a U such that C plus P at the next state is less than, or actually, let's put it this way. P at the next state minus P at the current state is less than or equal to minus C, and C is a positive thing. So it's a sort of reminiscent of a Lyapunov-like condition. We'll see how we apply it. I just wanted to give a little bit of intuition about why this, the first time that I saw it as a student, I said, where is this coming from? It's like some nightmare of a mathematician. So if all of this is satisfied, then the origin of the closed loop system is asymptotically stable with domain of attraction x of 0. Namely, your MPC control law, if started within capital X0, is going to asymptotically converge to the origin. So it works. We'll see after I prove this theorem how this actually leads to an actionable recipe to select the tuning knobs for your MPC, meaning how to select x of f, how to pick p, which is your terminal cost. But let's first prove the theorem. And the idea here is to come up with a Lyapunov function for the MPC control law and show that the Lyapunov function is indeed a Lyapunov function, so you have this decreasing property, which allow us to invoke the Lyapunov theorem to claim stability of the MPC control law. So the proof is as follows. This proof is quite cute. Is more interesting than the persistent feasibility proofs that personally I do not really like. All right, so as your colleague said, because of assumption A2, namely that the terminal set is control invariant, then MPC is guaranteed to be persistently feasible. We already proved that. Okay. Now, what I want to show is that J0 star x, which is the optimal cost of the MPC problem when initialized at x, it's just a function. It maps x into a number. That function is indeed a Lyapunov function for, valid Lyapunov function for the MPC control law. So that's our Lyap. If that is true, then we can invoke the Lyapunov theorem and show stability. So essentially what we're going to do next is then go step by step through the Lyapunov theorem, show that all its assumptions are verified, most importantly the decreasing property of a Lyapunov function for this very specific choice, and then invoke the Lyapunov theorem to claim stability. So let's do it step by step. First of all, let's write the closed loop dynamics as x, what do we use there, xt plus 1 equal f of closed loop of x of t. Remember that the f of closed loop of x of t is f of x, comma, the MPC law. Once I write u as a function of x through the MPC optimization, then I get a system that is just a function of x. Does it make sense? Once u is written as a function of x, I can then write everything as a function of x. That function, I just call it f closed loop. So first of all, we have to be disciplined. Is the origin an equilibrium point for the closed loop system? Closed loop meaning once we use the MPC controller as our control signal. Well, what does it mean to be an equilibrium point? It means that if you are at state 0, I solve my MPC problem, I get the optimal control, and then I transition into a new state that is equal to 0. Well, if I start at 0, assuming that u equals 0 is a feasible control, and remembering that our cost is a summation of quadratic terms where q and r are positive definite, what do you think the optimal sequence is that the MPC is going to optimize for? What is the result of the MPC optimization problem?
This thing at 0.
0. Because the cost is greater than or equal to 0. And if you start at 0 and use equal to 0, all this cost is going to be equal to 0. So 0 is a lower bound, and there is this actually u such that you achieve 0. So that's the optimal control sequence. But if you start at 0 and use control u equals 0, what is your next control? Your next state? 0, because aerodynamics are AX plus PU. So we just proved, at the minimum, that the origin is an equilibrium point for the closed loop system. Great. Then x0 is bounded and closed. That's a bit of a mathematical thing, not too important here. Now, what I want to claim is that the optimal cost, which is a legitimate function from the state to the real numbers, is indeed the Lyapunov function. So now we have to show all of the different criteria for J star to be a Lyapunov function, meaning has to be 0 at the origin, has to be positive elsewhere, and it has to decrease along the system trajectories. So let's start with the easiest one. So what is J0 of 0? So if you're at 0, we already shown that the optimal solution is u equal to 0 throughout the horizon, with corresponding cost equal to 0. Okay, that's an easy one. Also quite easy is to show that if you start at a state x different from 0, then the cost is going to be positive. Because remember that in your cost, you start from k equals 0. You go to n minus 1 of xk, k, k, k. So you have at least a term, x0 transpose q, x0. Since x0 is different from 0, and q is positive definite, at least the first term is going to be positive. Which means that if you start from a state that is different from 0, your optimal cost is positive. Okay. So to me, that's the easy part of the Lyapunov function. The harder part is to show that along the system trajectories, this function is decreasing over time. So basically, you are dissipating energy, you're dissipating cost, which means that over time, you'll get to the lower bound, which is your equilibrium. How do you show that? So let's consider an initial condition that is feasible, meaning that there exists a feasible solution to the MPC problem. Now, the terminology here is a little bit clumsy, but just follow me. So let u subscript 0 of superscript 0 being the optimal control sequence computed at the first iteration of MPC, iteration 0. And let denote the corresponding state trajectory as x of 0, which was our initial condition, x1, 0, xn 0, and so on. After we apply the first control in the control sequence, according to MPC, we transition into a new state, x1, that according to our dynamics is simply ax0 plus bu0 superscript 0. So far, no surprises. Now, let's see what happens now that we have transitioned into step 1. Let's consider a sequence of controls obtained as follows. I take the tail of the previous control sequence, and then I append a control V that is chosen to be a feasible control. And let's denote this corresponding state trajectory, the corresponding state trajectory as x1 is the point we're starting from. Look how the subsequent states are essentially the states that would have been predicted from a perspective of the first planning cycle, but starting from time 2. And the last state is simply given by AXN plus BB. Do you see this? So this is the part where terminology gets a little bit mixed up. Not mixed up, it gets a little bit confused. So basically, you have so at the first computation cycle, you have U0, 0, U1, 0, dot, 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 UN 0. And then UN minus 1. And then correspondingly, you start from state x0, you go into state x10, dot, 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 xn minus 1, xn 0. Okay. So now let's assume that we transition into the new state, x1, equal to a of x0 plus b u0, 0. Which means that basically you are transitioning to this state here. So if you now start applying this state control sequence, you will transition along the same states that you predicted from the perspective of the previous planning cycle. So that's what I'm trying to say here. And the last state, so the state that is one time step after, is AXN plus BB. So nothing particularly deep here, it's just a little bit of bookkeeping in terms of terminology. Any questions here? Yeah.
I guess why are we doing all of this if, like, I mean, the quadratic cost is convex, right? Can't we just argue that it's decreasing? So it's like a
well, we have to show that it decreases along the trajectories generated by the closed loop system. So it's not entirely obvious that when you evaluate the cost along those trajectories, the cost necessarily is going to decrease. Yeah. At least you wouldn't know a priori that that is the case.
Calculated based off of your initial state.
Yes.
But then that final control that you're implementing V, is that?
For now, this is just a V. The only thing that I'm saying is that it's feasible U. Now we'll show that for a more sophisticated choice of a V, I can find a control sequence that allows me to tell something about the decreasing properties of the Lyapunov function. For now, it's just a dumb, control sequence that I want to consider. On this note, let's be a bit smarter, and we know that xn0 belongs to xf. This is the terminal constraint for the MPC problem solved at step 0. Since xf is control invariant, I know that there exists a feasible control that allows me to transition back into xf. So now I'm refining the selection of V into the selection of a specific V that allows me to, for AX plus BB, to stay in the control invariant set X of F. That means that this control sequence is now a feasible sequence for the MPC problem starting at step 1. Why? Because V satisfies the control constraints, and the state trajectory is feasible in the sense that all of the states, x to 0, xn0, are going to satisfy the state constraints because of how the trajectory of step 0 was computed. And the terminal constraint is also satisfied because I've chosen V in such a way that the final state is in XF. So we satisfy the terminal constraint. So all of this to say that the specific choice of a control sequence is a feasible control sequence for the MPC problem at step 1. So now what we're trying to see is whether we can use this controlled sequence to say something about the evolution of the cost J0 along the trajectory. So essentially we want to say, is J star of x1 less than J star of x0? That's what we're trying to get to the point. Because if we can say that, then we can invoke the Lyapunov theorem. Now, for now, the only thing that we can say is that the J star 0 of x1 is less than or equal to the cost related to applying this candidate controlled sequence. Why less than or equal to as opposed to equal? Because for now, all we know is that this is a feasible controlled sequence, but it's not necessarily optimal. So the only thing that we can say is that the optimal cost is upper bounded by a cost of a feasible controlled sequence. Okay. Now let's add and subtract a couple of terms. So we add the P of xn0, we subtract it. We add the C of x0, u0, and we subtract it. Look at these three terms in red. When you sum them, what do you get? Remember that U0, UK superscript 0 was the optimal controlled sequence for the MPC problem from the perspective of stage 0. So when you sum those terms, what do you get? So here's the summation of the stage-wise cost. This is the terminal cost. So it looks like the cost of an optimal control problem. Which one? Exactly. +1 for your grade. Yes. That's exactly right. So all of these terms really correspond to the optimal cost, because we're using the optimal controlled sequence of the MPC problem solved from the perspective of step 0. So I can substitute from that. So those three terms are now encapsulated here. And then I have the remaining terms. Now we play the assumption 3, that Lyapunov-like assumption. The assumption 3 says that for all states in X of f, there exists a control, let's call it V star, with a property that AX plus BV star is in X of f. That's what V star does. Such that, let's go back. Let me write it here. I think it's. So we keep it here. It will also be useful later. So the minimum over U minimum over U in U such that AX plus BU is an XF of minus PX plus C of XU plus P of AX plus BU. All of this is less than or equal to 0 for all X in XF. So that's assumption 3. So now what I'm saying is that among all those V upper bar that allow me to transition into the control invariant set X of f, I pick the one that minimizes this quantity. And I know that the one that minimizes this quantity has the property that P of AX plus B bar minus P of X plus C of X V bar, all of that stuff is greater than or equal to 0. So for that specific choice of V upper bar, the three quantities in blue sum up to something that is less than or equal to 0, which allows me to derive the key inequality, whereby J star 0 of x1 is less than J star 0 of x0 minus this term here. Yeah, so basically I have J star x0 is less than or equal to, the star of x1 is 0 plus c minus c of x0 I'm serious of u0, 0 plus a term, and I know that the term is less than or equal to 0. So that implies that J star x1 is less than J star 0 x0 minus this quantity here. Does it make sense? Since this term, by assumption 3, I know is less than or equal to 0. Well, but C of x0 u0 is greater than 0 for all initial states that are not the origin, again, because the cost is positive for all states that are not equal to the origin, because of it's a quadratic cost. So we have just shown that the J star x1 is strictly less than the J star x0, meaning that the cost is indeed guaranteed to decrease along the system trajectories. So then we can invoke the Lyapunov stability theory and then claim that indeed the MPC control law leads to closed loop dynamics that are asymptotically stable, so are guaranteed to converge to the origin, assuming the assumptions are verified, with domain of attraction x of 0. Any questions here? I think that's an interesting proof. It's actually quite powerful. So try to go through it a few times just to internalize it. This is a fairly important proof. Okay, so now we have a theorem that allows us to reason in terms of persistent feasibility, a theorem that allows us to reason in terms of stability. How do we make those theorems actionable? Meaning, how do we link those theorems to specific selections for x of f and the terminal cost? Which in our case, we're assuming the terminal cost is quadratic. So we want to understand what this theorem tells us in terms of how we choose capital P. And we're going to see a couple of settings. So the first setting is we're given linear dynamics, but now A is asymptotically stable, meaning that all eigenvalues of A lie within the unit circle. So let's define XF as the maximally positive invariant set for the system xt plus 1 equal A of xt. How do you compute this positive invariant set? I'll show you in a couple of slides the link to a very handy toolbox to compute this set numerically. So you just use this MATLAB toolbox, write down a couple of commands, and you'll get this set. Now, x of f, as defined, is a control invariant set, since once you are in this set, since u equals 0 is a feasible set, then a of 0 is 0. So you stay there. So the persistent feasibility part is relatively straightforward. Now, how do we prove, how do we use the stability theorem? Remember what the stability theorem is asking us. Actually, let me write it in terms of a quadratic cost. So minus x transpose px plus x transpose qx plus U transpose RU plus AX plus BU transpose P AX plus BU. So we want this stuff to be greater than, less than or equal to 0 for all X in XF. So let's consider the specific control U equal to 0. The question is, for this specific control U, is this inequality satisfied? If that is the case, that's great. Then we can infer stability. Now, if you set U equal to 0, this term goes away, is equal to 0. This term goes away, this term goes away. So essentially, we are left with the inequality minus X transpose PX plus X transpose QX plus X transpose A transpose P AX less than or equal to 0. It just so happens that this is not a random matrix equation. It's actually a very famous equation referred to as the Lyapunov equation. And it turns out that if Q is positive definite and A is statically stable, there exists a positive definite P such that all this quantity is equal to 0, which satisfies this condition here. So what does that mean? That if you choose a P as the solution to the Lyapunov equation, and you are guaranteed that such a solution exists and is positive definite, so it satisfies all our stability theorem assumption, with that selection of P as a terminal cost, MPC is going to be asymptotically stable. So what's the intuition here? The intuition here is that basically you optimize MPC in such a way that after n steps, you end up, if you do nothing afterwards, into this O infinity set, and then you will let your natural dynamics that are stable to drive you to the origin. In reality, you won't do that, because by re-optimizing, you're always going to find some different control sequence. But basically, that set serves as an anchor to make sure that you stay grounded into desirable behavior. Mechanically, what do? You call a computational tool that I'm going to mention in a second to compute such a maximal positive invariant set, and then you choose a P in order to solve the Lyapunov equation. It's another one-line command in MATLAB. You plug those numbers into your MPC, you're guaranteed persistent feasibility and stability. So what if A is not stable, meaning that your natural dynamics don't help you with going to the origin without control? Well, that means that you have to do active control in order to make sure that you go to the origin. So in this case, you still have a similar procedure in order to tune your parameters, but you now use LQR, active control, as basically your controller that allows you to anchor your future dynamics into some dynamics that will lead you to the origin. Specifically, let F infinity be the optimal gain for the infinite horizon LQR controller. Set X of F as the maximal positive invariant set with respect to the LQR closed loop dynamics, which means that after n steps, when you hit set X of F, if you don't do any replanning, at least you have a feasible LQR controller that allows you to stay within the set X of F. But then, if you choose the terminal cost P in such a way that your LQR controller would essentially brings you to the origin, then you are guaranteed to be stable. Now, here the derivation is a little bit more convoluted algebraically, so I'm not going to show it. But essentially, the style of reasoning would be the same. We plug the controller, the LQR controller, U equal F infinity X, into this inequality. And then we will show that if we pick P as the solution of this equation, then we will have equality. So we will satisfy the stability condition. And this equation, again, is not a random equation. This is the Riccati equation, and is guaranteed to have a solution. So bottom line, if you have an unstable system, you pick your terminal set as the maximum positive invariant set for the closed loop LQR dynamics. You pick P as a solution to the discrete time Riccati equation. You plug those numbers into your MPC controller, and then you're guaranteed to have persistent feasibility and stability, and you'll have a couple of problems in your PSET. Now, these are not necessarily the best possible choices, but just some choices that are very procedural. So if A is stable, maximally positive invariant set with respect to the uncontrolled dynamics, choose P as the solution to the Lyapunov equation. A is unstable, choose your terminal set as the positive invariant set for your LQR closed loop dynamics, and choose P as a solution to the Riccati equation. With the idea, again, that you basically carve out a region X of F where the optimal unconstrained controller is considered to be feasible, and this is used as a value function to guarantee stability. Right, that was quite a bit. Let me conclude with two very quick things. So the first one is that so far we've been looking at MPC through the lens of online optimization. So measure a new state, you solve an optimization problem online, basically on your device, get a control sequence, you apply the first control input, and then you re-optimize. Now, it turns out that there is also an explicit / offline version of MPC that allow you to pre-compute the MPC control law such that you don't have to do any optimization online. To appreciate that, let's go back to our usual setup. By the way, MPC can be generalized also to nonlinear systems. But here, the goal of this class is to give a broad overview of different control techniques, so we'll only discuss it in the context of the linear system. It is already quite interesting. So we're back to, usual setup, linear dynamics, quadratic cost. So it turns out that the solution to the constrained LQR problem is a control, which is a continuous piecewise affine function on a polyhedral partition of the state space that is, there exists a partition of the state space so that if, say, in 1, 2, 3, 4, 5 regions, such that if your initial state for your MPC computation is here, you can just look at a lookup table, and then the optimal control policy is simply f of x plus g, where the fkj and gkj are gains associated with a specific region. So basically, the solution to LQR is just a piecewise affine control, which allows you to basically do a lookup table search online, meaning that you measure a state, you'll see in which region the state falls, you pull out the gains corresponding to that region, and then you have your optimal control law. There is no optimization that you have to do online. And these terms, F and G, and the partition of the state space is all computed offline. I'm not telling you how to do it. I'm just saying that this can be done. So you say, great, why don't you do it all the time? This is great for a number of reasons. Basically, it avoids you to solve an optimization problem online. Solving an optimization problem also has its own challenges beyond just how quickly the optimization problem can be solved. For example, you have to show, say that you are in a safety critical situation. You want to land a rocket on Earth. Well, it means that you really trust your optimizer not to have bugs. So from a development program standpoint, it has costs. You need to have additional people that have to write the optimizer, they have to customize it, they have to code it into an embedded environment, you have to validate it. Here, everything is explicit, so the validation step is much easier. On the other hand, it turns out that oftentimes this polyhedral partition of the space takes very weird shapes. Meaning that you have a lot of cells. And today, the optimizers, such as the convex optimizers, have become so good that oftentimes it's faster to just solve the optimization problem rather than just doing a lookup table in a gigantic table. So explicit MPC is a good concept for you to know, with understanding that oftentimes you just use online optimization these days. So we essentially discuss the famous multi-step design process for MPC, where we choose, you can also play a little bit with horizon length. In this class, we focus primarily on XF as your tuning knob for persistent feasibility. So you tune XF to be control invariant so that you have persistent feasibility. You choose the parameters Q and R freely to affect the control performance. You adjust capital P as per the stability theorem, and then you have an automatic way to tune your MPC algorithm. To compute these control invariant sets and so on, there's a very handy toolbox, which is MPT3, and that's what you will work with in your PSET3. One last thing in the past 4 minutes. So far, we have looked at MPC as a tool in order to achieve stability. So basically, you want to make sure that the state converges to 0. But oftentimes, you want to use MPC for tracking. So basically, you're giving a reference trajectory, for example, computed through a direct method. And then you want to use an MPC wrapper that basically allows you to counter-react any disturbances and make sure that your actual trajectory stays close to the reference trajectory. So the most naive way of setting up the tracking problem is to have a cost where you penalize deviations from your reference trajectory plus a quadratic penalty for the control effort. So this formulation does not work. The reason why it doesn't work is that oftentimes, to track a reference trajectory, you need non-zero control. So say that you have an aircraft and you want to track a constant altitude profile, you can't really switch off the engine. You still need like a constant thrust. So what happens if you use this formulation is that at the moment your tracking error goes to 0, now the cost is dominated by your control effort. So now MPC is trying to minimize the control effort. So basically, you reduce thrust. And then your tracking cost goes up. So you start going to these kind of oscillations in between control effort and tracking error cost. So what's the solution? You reframe the problem in terms of delta controls. So basically, how you change controls with respect to time steps as opposed to absolute control. So you frame the tracking problem as a problem of minimizing tracking error. So y is c of xx. I mean, c could be also the density, could be just xk minus rk, where r is your reference, plus a penalty term with respect to the deviation control variables, where the delta u's are defined as a uk minus uk plus minus 1. So that in perfect tracking, what you have is a 0 tracking error and a constant control, meaning constant thrust, which means delta u equals 0, which corresponds to what MPC really wants to do in this formulation. So all this to say that this is a better version. There are other considerations to take into account for tracking, but just to give you some intuition about how for tracking you want to be a little bit more sophisticated in how you set up the MPC problem. In particular, typically you want to use reason in terms of delta controls. So the optimization variables are the delta u's that are defined as uk minus 1. You are given the u at the time t minus 1, and then you obtain all the u's recursively by adding the delta u's that are really the optimization variables. Does it make sense? All right, so we did quite a bit. So this lecture essentially wraps up the first part of the class, where we assume that everything about the model is known. Starting from next week, we'll go into the new setting, whereby the model may not be completely known anymore. So either you have to adapt to the part of the model that is unknown, or learn what you do not know in order to still act optimally or very close to optimally. So P3 will be an interesting one. So we'll expose you to a lot of these MPC ideas, and we'll also force you to work with the MPT3 toolbox, which is kind of neat. All right, so see you next week.